Power series. Essential question. What is a power series? And can we identify the interval of convergence for a power series? First, let's talk about what an infinite series is. And an infinite series has this expression. Notice that different from a sequence, it's not only a list of numbers, but this list is being added together. Let's take a look at a very special sequence, and this is what we call a sequence of partial sums. This is a list, S of 1, S of 2, S of 3, S of 2, S of n, but each item in the sequence is really a sum, and a sum that adds an additional term each time from the previous sum. So we call this a sequence of partial sums. Now, it's important that we understand that this is what we're going to be working with a lot. We're going to be working with a sequence of partial sums, which is going to describe a series. And when this converges, we say that this sum converges to some limit L. And if the sequence of partial sums does not converge, that means it's not approaching a limit, and we say it diverges. Let's take a look at an example of some partial sums so that you can see the difference between converging and diverging. Notice that I wrote the partial sums, the first partial sum, the second, the third, the fourth. We say this diverges. Notice that these partial sums aren't approaching a limit. Now, in contrast, this partial sums look like they're getting closer and closer to 0.7 repeating, and 0.7 repeating is 7 ninths. Now, notice something important about this. Each term in the series is getting smaller and smaller as n approaches infinity. So as you increase the number of terms in here, each term that's being added is getting smaller and smaller. So if the infinite series converges, you have to understand that each term that's being added is smaller and smaller and smaller. That's the only way it can happen. But the converse is false. Now remember what a converse is. It's when you exchange the hypothesis and conclusion. So just because each term is getting smaller and smaller doesn't mean that the whole series converges. And to convince you of that, I have to give you a counterexample. And a counterexample is something like this one right here, the harmonic series. This is a harmonic series 1 plus 1 over 2 plus 1 over 3. I want you to notice that each term, as we add it, is getting smaller and smaller and going to 0. But in actuality, this series is getting, the partial sums are getting larger and larger and larger. And the way to convince you of that is to remind you that this is very similar to the integral from 1 to infinity of 1 over x dx, this improper integral that we've talked about before. And this improper integral diverges through the p-test because that power, x to the power 1, is diverging. Let's take a look at a geometric series. And a geometric series in your past studies, the infinite series will converge to a specific sum as long as that ratio between the two terms in a row is going to be less than 1. Now here's the proof. Let me remind you of the proof. S of n, this is a geometric series. I'm going to take this series and I'm going to multiply it by negative r. So I'm going to take this term, I'm going to multiply it by negative r, and it'll become this, and I'll put it under this term. Now I'm going to take this, and I'm going to multiply it by negative r, and I'm going to put it here underneath this common term, and so on. I'm going to take the last figure, multiply it by negative r, and it becomes this. Now I'm going to add these two together, which means adding these representations together, and I will now get this term here and this term here, and all the rest will go to 0. Now I'm going to factor out the s of n, I'm going to factor out the a, solve for s of n, and this is the sum of the finite series. Now I'm going to take a look at the limit of s of n as n approaches infinity, and I'm going to take this portion, the limit of this factor, times the limit of the remaining factor, and right here, this is the only factor that has n in it, so that's affected by n approaching infinity. The only way this is going to have a limit is if this part right here goes to 0. And it's going to go to 0 as long as the ratio is a fraction between 0 and 1. So for instance, if the ratio is 1/2 and you take it to a very high power, like 100, you see that that's approaching 0. So this whole thing will approach 0 when r meets this criteria. And then this whole limit will be 1. And of course, there's no n in this expression, so it's a over 1 plus 1 minus r, and then this limit will be 1, and so it's just going to be this answer. This is the formula that we teach you for a geometric series. Okay, see if you can find the sum using this formula that you were taught before. And here's the answer. You have to first notice it's geometric. You have to notice the first term, which is 5, and you have to make sure that it meets the stipulation of convergence, which it does when r is equal to 1/2, and then you can use the formula. Over here, it's geometric, and we can see that the first term is 1, that the ratio is 3/2. It meets the stipulation of the ratio, and therefore we can use the formula. Now we call this a series of constants because what we're doing is it's just a lot of constants being added up together. So this is 3/5 to the 0 power plus 3/5 to the 1 power plus 3/5 to the 2nd power, and so on. So we're just adding a lot of constants here.